Greetings and welcome, friends. We are back in section 3.2. We have been talking about linear functions. If you missed the first part, I'd really recommend you go back and watch it because you're missing out on some gold, friends. Gold. But this part's going to be A-okay as well. So here we go. We're continuing 3.2. Big ideas, Algebra 1. Here it goes. A solution of a linear equation in two variables is an ordered pair x, y that makes the equation true. Okay? The graph of a linear equation in two variables is the set of points x, y in a coordinate plane that represent all solutions of the equation. Sometimes points are distinct. All right, think disconnected, all right, discontinuous, all right, and other times the points are connected. Okay, so here's some one-dimensional examples of discrete and continuous domains. What do you think they mean by domains there? Domains were a domain was the set of possible input values. Okay, here we go. A discrete or disconnected domain is a set of input values that consists of only certain numbers in an interval. So integers from 1 to 5, notice I said integers, so that does not include fractions or decimals, would be the numbers 1, 2, 3, 4, 5, and right, those are discrete disconnected points. I don't have variability in between there. It's only those values. So this is I almost actually would describe this, if the term, I don't know if it helps you, digital, as far as right, they are distinct values. Let's see, what's a digital example? Well, we'll get to some today. Let's see, a continuous domain I would call analog. All right, okay, here we go. A digital example would be shifting through the gears of a car. All right, I can't be in 1.5 or 2.7 gear. I can only be in gear 1, 2, 3, 4, 5. Whereas analog maybe is the like the variability, the degrees at which I can press my foot on the accelerator, right, the gas pedal. That I could have it, right, part way down. It's not like a series of notches that it only is a set amount. I actually have like variable control over that in between all of those values. Theoretically, if we were talking about the accelerator on a car, 0 would have been a legitimate position because it's not. Hopefully, your car isn't like forced to be accelerating. That wouldn't be good. Let's see. So a continuous domain is a set of input values that consists of all numbers in an interval. So all numbers from 1 to 5, or all real numbers from 1 to 5, right? I include all of these little values in between. There are infinitely many numbers here. Here there are only 5 numbers, okay? Now this includes the 5 from up here, but it also includes the infinitely many values in between ones. So let's see. Let's look at graphing discrete data. All right, here we go. Oh, man, I blurred the screen. I used my wrong screen capture tool. That's okay. That's all right. Little behind the scenes, I use a couple different screen capture tools as I'm copying and pasting. It says, let's see, example 4, graphing discrete data. Says the linear function y equals 15.95 represents the cost y in dollars of X tickets for a museum. My friend used to make fun of me because I said museum. I don't know. Is that weird? That's probably weird to call it a museum, right? Because I mean, if you think about it, what do you do at a museum? You go to see them, right? You go to see the things there. You got to go see them. You got to go see the museum, right? So that's how I kind of lamely remember how to say. I just said museum. Ah, blast. So let's see. Find the domain of the function. The question is the domain discrete or continuous? Okay, so what is the domain of the function? Let's see, part A. The domain are the possible input values. Is it possible for me to buy half of a ticket to the museum? No, right? I can't buy 2.37 tickets to the museum. So my domain is the set of x such that x is which of the following? Let's see. It says you can buy up to 4. So I could buy, actually maybe I'll even get rid of the set of all x, but I'm going to buy 0, 1, 2, 3, or 4. If you still had the set of x there, you could just write this after that. That'd be fine. So it's the set of all x such that x is 0, 1, 2, 3, or 4. I can't buy the values in between there. So this is a discrete set of numbers. All right? Discrete. So depending on the problem that I'm solving, I've got to figure out, is it discrete or is it continuous? And my explanation verbally is because I can't buy fractions of museum tickets. All right, let's see. Then it says this, challenge for us. Graph the function using the domain. All right, let's see. Let me grab a snapshot of a grid. I don't know if I gave you guys a grid. My apologies. My sincerest. We did? Oh, awesome. Man, good job. High five, past self. Oh, that's sad. I can never high five my past self. But it is possible. I don't know if you guys thought about this. Your past self can initiate a high five with your future self. Right? If you think about it, if you like have one hand up and then like you accelerate your other hand so fast that like as it's going there, like your future self can't stop it because of the force. You're just like, oh, and I tried to pull it back, but I couldn't. Right? My past self gave it so much force that my past self was able to initiate a high five with my future self. Pretty good. Thanks, past self. I appreciate it. I needed the encouragement. So let's look at this. So one of the ways we could do this is making an input-output table. So I'm inputting X. I'll have a column for work. I'll find out what Y is. And then in this case, because I want us to become a little bit more familiar with it, we'll also then write it as an ordered pair, X, comma, Y. Y. All right, so my possible X values are 0, 1, 2, 3, 4. And let's see, for my work, what does the function tell me to do? Does anyone remember what the function was? The function was y equals 15.95x. Let's see, where x is the number of tickets purchased and y would be the total cost because I'm multiplying the price per ticket times the number of tickets. So those, yeah, would just equal a dollar amount. So, all right, so here we go. So 15.95 times 0 is equal to what? 0, that's easy. So as an ordered pair, that's 0, comma 0. All right, 15.95 times 1 is going to be 15.95. And that means 1, comma 15.95 will be our value. Let's see, plug in 2, so I'll have 15.95 times 2. And in case you guys didn't know, that's 31.9. That's 2, comma 31.9. Good, good. Let's see. Let's keep doing it here. We're on a roll. I'm gonna go to the museum. 15.95 times 3 happens to be 47.85. Right. So as an ordered pair, that is the input was 3, the output was that. So write it as an ordered pair. 3, comma 47.85, 85. And lastly, 15.95 times 4, if I evaluate that, happens to be 63.8. And so I'll have 4, comma 63.8, the maximum value for my graph. So for my graph, okay, let's see. So my x-axis is here, My y-axis is here. Let's take a look at our x values. I go from 0 through 4, right? Those are all my x values. So I've got 10 slots here on my grid. I don't know if I gave you the same one, but I'm going to count by twos. Or sorry, I guess I'm counting by halves. So every other block I'll label as 1, just so I've got space. And actually, I won't even end up using the rest of that. Okay, for my y values, my smallest one is 0. My biggest one is 63.8. Ooh, boy. So maybe we should count by tens. So 10, 20, 30, 40, 50, 60, and 70 is about as high as I need to go by the looks of things. So now if I want to plot these points, I'm gonna plot them. So let's see, 0, 0 would be at what's called the origin, right there. Or I could buy one ticket for $15.95. So let's see, so over 1 and up, that's 10. 20 is too far, so a little bit more than halfway. You guys agree? Right, so around $15.95, 15 would have been the midpoint. So I'm going a little bit above that midpoint. Let's see then, 2 tickets was $31.90. So over 2 up to 30, and 1.9. So I'm thinking like 19% of the way between 30 and 40. I don't know, something about there. And let's see, then I've got 3. So over 3 and up 47.85. So 78.5% of the way between these two values for my y. So I don't know about there. All right, I'm just doing the best I can. And let's see, 4 and then 63.8. So up to the 60 line is here. 70 is there. So 63.8 is going to be like 38% of the way there. So did I mess up somewhere? Guys, this point looks wrong. Look at my point is between 50 and 60. It was supposed to be that. Uh-oh. I hope you guys didn't mess up. See, it's supposed to be right here. My apologies, friends. Maybe you didn't make the same mistake I did. Maybe you did have it correctly between the 50 and 40. And let's see, so 4 and then, 63.8. So my solution set are these points, and each of these points represents an ordered pair, right? So this is the ordered pair, 4, 63.8, which means that if I purchase 4 tickets, it will cost me $63.80. All right. So let's look at example 5 here. Yeah, see, this problem took a little bit more time. I'm glad we are spending 2 days on this instead of just 1. That would have been craziness. I think you would agree. All right, but you see, we made a table of values. I plot the points. This was a discrete situation because I couldn't buy fractions of tickets. Yeah, I do have graph paper here as well if that is something you wanted. All right, cool. All right. Ooh, a cereal bar. I might have one for snack. Delicious. All right, here we go. It says a cereal bar contains 130 calories, which, by the way, like 2,000 calorie diet is normal based on what they say, apparently. Or 2,500, sometimes I've seen up that high. Oof, boy. Let's see. The number C, so there's my variable, of calories consumed is a function of the number B of bars eaten. Does this situation represent a linear function? Explain. Linear function. Is it going to be a constant rate of change, do you think? Let's see. So for A, as B increases, for every 1 bar I eat, how many more calories do I get? What do you think? How many more calories do I get for every 1 bar that I eat? I get an extra, thoughts? 130 is the answer to the question I was asking. 130 calories, and that's a constant rate of change. All right, so this is constant. and therefore it is linear function. Okay, let's see B. It says find the domain of the function, and is the domain discrete or continuous? Okay, so for my domain, it's going to be the set of all x such that, let's see, can I eat 0 bars? Well, I mean, I know maybe according to my self-control, no, but theoretically 0 bars is a perfectly good number of bars to eat. Can I eat negative cereal bars? Um, uh, well, no, I'm going to just say no. Like, I mean, even if I was to throw one up for some reason, I would have had to have eaten one at some point. So hopefully it's not ever going to be negative. Can I eat half of a cereal bar? Yeah. Yeah, I could eat half of it. I could eat 2/3 of it. I could eat 72% of it. So I think, and then could I eat a million cereal bars? Uh, if you wanted to, if you're committed. So it looks like all positive numbers, even fractions, and then also 0 works. So I'm going to say it's the set of all x such that x is greater than or equal to 0. And because this includes fractions and decimals, this will be a continuous situation, right? Because there are situations where maybe I'll eat 1 1/3 cereal bars, and then my kid's looking at me with his sad eyes, and I'm like, fine, you can have the remaining 2/3 cereal bars, right? And then I'd give it to him, maybe. Okay, all right, so let's look at part C. Let's make this input-output table. Part C, and then, oh, we're going to graph it. Let's see, so I'll have x, I'll have y. There's really not much work to do in this case. So let's see, so I could have 0. We'll pick some values. Actually, we'll pick the same values we did last time. And so if I eat 0 cereal bars, what do you think that would, how many calories would that be? 0. If I eat 1, I get 130. If I eat 2, I get 130 more than that, so that would be 260. If I eat 3, I get 130 more than that, so that would be 390. If I eat 4, it's 130 more than that, so that's 520, etc. Okay, it's etc. All right, right. Let's see, did I copy? Let's see, I think I can use the same grid that I had for the last one. We'll talk about it later, because we want to be successful in math class right now is what we're working on. That's what we're doing. Let's see, so let me pull in this graph. Well, but not as important as this right now. So don't you worry, don't you worry. So let's see, if I want to graph this. Now, I'll count by ones for my x-axis in this case. Because this keeps going forever, and so does this. All right, and let's see, for the y-axis, maybe I should count by hundreds? Does that make sense? Let's see, 6, 8, I'm just labeling every other one, but these are counting by ones, notice, because this would have been the 1, this would have been the 3. But I'm not going to bother labeling all of them. And then let's see, for this, I'm going to label, you're awesome. Stick with us, man, because you're going to know how to do this. I know you're distracted, but I need you to focus on math right now. Help me, friend. Help me. Let's see. So you had an interesting idea. We theoretically could count by 130, and that works out nice because I did happen to have zeros as my beginning value, as my origin. But let's see. I'm going to count by hundreds. So let's see. And I might only label every other. So 200, 400, 600, 800, 1,000, right? Something like that. So let's plot these points. I've got 0, 0. I've got 1, 130. So that's going to be 30% of the way between 100 and 200. I've got 2 and 260. So that'll be, let's see, 200 and 300 right here. Let's see, 3 and 3, 90. And 4 and 520. So 500 is right here, so 20% of the way, something like that. And now this was a continuous function. So behold, I can actually line up my points and draw a line, because it's also a linear function. And all of the solutions, gorgeous. Gorgeous line. I like having my ruler tool now. I haven't used that for this year. So all of the points on this line are legitimate solutions to this problem, okay? Where I could say, like, how many calories do I get if I eat 4.5 cereal bars? 4.5 cereal bars, well, I'd go over to 4.5 and I'd look up here, and it looks like somewhere around 600 calories. Right? Or if I want to eat 6.2 cereal bars, I would go up here, I'd track that, and it looks like that would be around, let's see, you can't see that color at all. 6.2 comma, I don't know, maybe that's like 820-ish, right? So all of these points on the line are possible solutions of this equation. All right, let's see, last problem. Last problem. And Austin, please stick with us, friend. Yeah, but you're missing out. You don't know, man. Okay, here we go. Oh man, oh dear. Write a real-life problem to fit the data shown in each graph. Is the domain of each function discrete or continuous? Explain. Okay. Real-life problem. Well, okay. Well, let's look at this one. Is you're saying what? Well, this one is discrete because it's got points. Then they're not connected. And this one over here is continuous because there's all of the points are connected. All right. And now, if I wanted to come up with like a sample situation that did this, let's actually first look at what the rate of change would be. So this one is down 1 over 1. Okay. So for every 1 that this x increases by, I lose one of these y's. Okay. So x. Let's see. Here's one of the book's ideas. They said if x is the number of times you play a game. Okay. Number of games played. And let's say y is equal to like the number of quarters you have. All right. So notice, right, you'd start with 6 quarters when you play 0 games, but every game you play, you have 1 less quarter. Okay? So something like that. And this would be a discrete situation because you can't pay with 1/3 of a quarter, right? Or 72% of a quarter, right? That doesn't make sense. Okay? Over here, this is continuous. This has got the same rate of change. It's going down 1 over 1. But I could also go down 1/2 over 1/2. All right? And let's see. So an example of this could be x is equal to, what do you guys think a continuous situation would be? Continuous. We had, I mean, like the other day we had like gulps from the orange juice or whatever it was, right? That was this class, I think. Right, so you could theoretically have a weird number of ounces in a glass. So if x was like the number of gulps, and y is the number of ounces in a glass, right? That's a continuous situation because I could, or I guess if I do like, 1/2 of a gulp, I could still have, 5.5 ounces of fluid in the glass. A sample answer that the book gives is the cost of a taxi ride is the y value. Actually, wait a minute. That is 50 cents per mile plus a $2 fee. It runs along a 6-mile portion of the city. That work? Well, that is a continuous situation because you could drive like, fractions of a mile. Let's see. 50 cents per mile. So it's costing your cost is 50 cents for every. No, I don't think their example works. But this would work like the number of miles you drive, and then the amount of money you have goes down $1 for every mile, something like that. But anyways, I think I'm happy with that. Well, thanks for watching, internet friends. I hope you have a great day.